Okay. Okay. It doesn't matter. Can go on with this. Don't worry. Okay, hello everyone. Thank you, Abda, for the introduction. In this presentation, we will explore why process modeling is essential in advancing CO2 capture technology, focusing on rotating packed beds, also known as RPBs. I will walk you through the development, validation, and operational analysis of a custom model, focusing on the use of amines as the solvent. But first, we need to address why do we need process modeling? A model can help us understand the underlying system of a physical system, the underlying phenomena of the physical system. It can serve as a predictive and design tool for scaling up applications. Moreover, simulations are far more cost-effective than building physical prototypes, especially during the early stage of an application's lifecycle. Modeling has several key characteristics to be essential. It has to be accurate in order to ensure precise representation of real-world applications. It has to be flexible in order to adapt the operational conditions for every case study, and it has to be efficient. It has to be combined the high computational speed, while at the same time requires minimal resources. The steps of developing an RPB model for carbon capture starts with understanding the primary goal of the model. In our case, we have developed a model capable of designing an RPB in different conditions for industrial application. A model has to gain a detailed understanding of the underlying phenomena. For RPBs, we have incorporated phenomena to evaluate the centrifugal forces inside the reactor, the gas-liquid interactions, and the reaction kinetics involved. Then we move to select the appropriate modeling approach. We have a first principle modeling approach, which combines a mass and energy balance equations. The next step is to actually develop numerically the model, the solver of the system. When all of this has already complete, we move on to validate our predictions with experimental data in order to see how far we are from the experimental conditions. A sensitivity analysis is a vital tool in order to identify the key factors that affect our process. And finally, when we have the model, we can use it as a base case for optimization algorithms or in further analysis like life cycle assessment or heat pump integration, as you will see in the upcoming presentations. We have already mentioned by previous presenters the carbon capture process. This conventional configuration with one RPB absorber and a desorber with an external reboiler, just to illustrate the key components of the capture process. The absorption unit has the requirement to capture up to 90% of the incoming flue gas, while the regeneration is responsible for reducing the amine solvent for minimal losses. We have already explained why an RPB technology is necessary for this kind of applications. To summarize, it's a process intensification device which results in 10 to 15 times more compact design, as you can see in this figure. It also has higher flooding limits, and you can use higher viscous solvents to do it. And also, it can expand the scope of potential applications, maybe to marine transport and more. Here we have a more detailed view of how an RPB works. We can see the packing and the casing of the RPB when the feed gas is introduced into the outer radius and the lean solution is introduced into the inner section. We have a counter current flow arrangement because it greatly enhances mass transfer rates compared to co-current and cross flow configurations. And we can see that as the liquid moves from the inner to the outer section, then it breaks into tiny droplets until it reaches the casing wall, where it accumulates to form a film, which is important in the absorption rate. We have to identify the state of modeling. We have to make a choice about the combination of mass transfer approach combined with the reaction kinetics involved in the process. There are several mass transfer theories. For example, it's the penetration theory, two-film theory, and the surface renewal theory. We have chose the two-film theory because we can detailed represent the occurring phenomena inside the reactor. Both of them have limitations and benefits, so we make the choice for two-film theory. We have a rate-based model, and the choice is about the CO2 reaction kinetics. In conventional packed bed reactors, we use often equilibrium assumptions, but in an accelerated process like RBB unit, we have to incorporate kinetics into the model. The kinetic model can be simplified using first-order reactions and an enhancement factor to quantify these chemical reactions. This graph illustrates the complexity of a model with a combination of the mass transfer approach and the reaction kinetics, with level 5 stands out as the most accurate one. Now, what we propose a model, a custom model without the use of commercial software, and it was developed for both packing and cavity section model. It is operates at the level 4 of complexity with a rate-based mass transfer and enhancement factor for chemical reactions. As I have already explained, it is a first principles model and combines both and integrates both the CO2 absorption in RBB and the regeneration system. It has all the occurring phenomena inside with mass transfer, heat transfer, and a pressure drop equation, which is a vital equation for the system's performance. And also it has an increased flexibility because it can operate at both co-current and cross-flow configurations. The methodology used for designing an RPB starts with packing specifications, which, as Professor Lee explained, we have to identify the void fraction and the specific surface area for its packing. Then we move on to process inlet streams. For example, for the absorption, we have the lean solution and the feed gas, which enters the RBB. It is essential to choose the appropriate thermodynamic model with the occurring enthalpies of reactions of reactive absorption or desorption. We have equilibrium pressures with respect to loading and temperature, which is vital in order to have an accurate model for this type of processes. As we have said, mass transfer theory is important to understand that we have to incorporate mass transfer correlations that is relevant to our process, which is a difficult part of modeling approach. And also we have material and energy balance equations that we have incorporated in the model. It acts as the base, the foundation of our model. Of course, every modeling method has some basic assumptions. We have assumptions for both the absorption and the regeneration. At this point, we operate at steady state operation with a counter current flow arrangement, an ideal gas phase assumption with CO2 water and the amine and the nitrogen in the absorption. And a critical assumption that we assume that chemical reactions take place in the liquid film, and this is the part that we address this phenomena. And also end effects in the cavity zone are accounted in the absorption process. A set of 5 ordinary differential equations form the foundation of our model. Material and energy balance equations, as with the pressure drop equation, as you will see later, form the foundation. We have here the energy balance for the liquid phase, where we account the critical term of the reactions of the enthalpy of the reaction into the absorption, while the heat transfer between the liquid and the gas phase, along with enthalpies of condensation or vaporization inside the process. Gas phase temperature is directly linked to the liquid phase temperature by the interfacial heat transfer coefficient. And finally, gas pressure drop are accounted in the model, with including terms of centrifugal acceleration, Bernoulli's principle, and frictional losses within the piping material. Each equation, of course, has their boundary conditions, which are responsible for a valid operation of the model. To be more precise about our custom solver, we are using the suiting method, which is a transformation of a boundary value problem into an initial value problem in order to solve the model from the inner to the outer range. So we numerically solve the radial dimension from inner to outer until we meet the desired level of accuracy. And also, this model has a specific custom for this type of operation in order to be flexible, accurate, and efficient. This is another figure that illustrates the structure of our iterative approach. We have the initial parameters, the guessing parameters, and also the ODE solver. And then we have the convergence criteria where we check the guessing values with the predictive ones, and then a new iteration begins for another outer radius estimation until we meet the 90% of the capture specification. When we have already the model, we have already incorporated a simulated annealing optimization algorithm, which is a robust tool for such complex processes. We have formulated the objective function in a cost minimization approach. And as you can see, this is the total annual cost, euros per years, normalized by the capture ton per year. Optimized parameters will be the rotational speed for each RPB unit. It will be the reboiler, pressure, and temperature, among other factors, like the liquid to gas ratio into the absorber. Developing a model has challenges in order to be precise in real-world applications. The biggest challenges that were faced in developing the model, the first one was to account the rotational speed into the mass transfer coefficient, because literature has a lack of available mass transfer coefficients for this type of operation. So it was a time-consuming task, because we had to identifying the operational range of its correlation and test it appropriately into our specific system performance. And also the generational process, it was quite challenging stuff, because there's not a lot of foundation in the regeneration process in literature. Of course, we have validated our model based on published data from Newcastle University. We can see here that we have a mean absolute deviation of 4% for output CO2, gas CO2 mole fraction. We test in 20 different case runs, and we can see that the model exhibits very good results in terms of comparing experimentals with the predictive results. And also we have assessed rich solution temperature with a deviation of 2.2%, which is quite close to the experiment. Here we can see the absorption process inside this RPB. We can see that as the flue gas enters the system, the CO2 begin here in the cavity section, where it has a decrease. Then it stabilizes, because this is where the tiny droplets forming, and then we have the packing region where it's happening the absorption profile, as we can see. And liquid temperature mirrors the absorption pattern, because for every molecule of CO2 have the exothermic reaction between CO2 and the solvent. Then we move on to validate our regeneration process based on published work from Cheng on 2013. We have assessed lean loading and reboiler duty. This was the only published work with a combination of an RPB desorber with an external reboiler combined. So we have validated through 7 case runs with a mean deviation of 2.5% for the lean loading, and for the reboiler duty, a deviation of 3.7%. We can see here the regeneration process analysis with 3 occurring phenomena of heat of reaction to release the loaded CO2, the sensible heat needed to increase the temperature of the rich amine in the reboiler, and the heat of water vaporization inside the reboiler, which will be used as a stripping medium in the RPB desorber. And we can see that this is experimental runs, and this is a model predictive. So it's the variations, it has very good agreement. And finally, we tested the operational analysis of our absorber unit based on KOLAS flue gas in order to test how the design, how the operational parameters affect the design of our RPB. 30% of MEA aqueous solution was the inlet lean stream, and we set the capture efficiency was set at 90%. 2 vital variables, rotating speed and liquid to gas ratio, was changing from 400 to 800 RPMs and from 3 to 5 kilograms liquid per kilogram of gas. And the results on the left figure shows that as the rotational speed increases, the packing volume decreases with a steep gradient. And we can see that the axial length also decreases as we have more enhanced mass transfer rates. And on the right figure, we can see that as we increase the liquid to gas ratio, also the packing volume decreases, but the axial length, it slightly increased because we have a more viscous solvent. So the correlation for estimating the axial length is, it needs more required space. To conclude, we have developed a custom model to simulate all the phenomena that occurs inside these 2 reactors for a solvent-based CO2 capture process. We have validated with experimental data, which makes the model reliable and effective. And also, we can say that we have integrated also MEA solution and CDR max solvent, which is part of the scope of this project. And it's highlighting the ability of using different solvents. We conducted an analysis to key operational parameters in order to test how the impact they have in our design. And finally, utilized a steady state optimization algorithm to determine the optimal operational conditions. The acknowledgements, and that's all for me.